Hi everybody, and welcome to Module 3. In this one we're going to start our discussion of physical geography by looking really at the landscape, really some geology here. What creates the kind of landforms that we see in the world, the valleys, the mountains, these sort of things, and what kind of processes make them. And so in this video we're just going to be focusing again on 4 major points. Of course, you need to make sure you go through the rest of the chapter and the PowerPoint and the discussion questions to make sure that you're kind of getting the fuller picture here. But what I'm going to focus on in this lecture is the 4 key points of looking at the structure of the Earth, some of the basics on tectonic plate movement, and then focusing a little, generally on the processes that build landforms, things like volcanism or uplift, and then also the processes that wear down landforms, like erosion, whether it's caused by water, by wind, or by glaciers. And so, while in this lecture I don't go into a lot of the big specifics about things like volcanism or associated things like earthquakes and tsunamis and that kind of stuff, which is in the book as well as in the rest of the PowerPoint, I go over some of the basics in here. Same thing here with the discussion of erosion, and also the video, looking at that video on the landscape of Hawaii, gives a great example of how these processes work, how landforms are built as well as how they are torn down. Okay. So, just as an introduction here, one of the words that's important to understand is what's called geomorphology. And geomorphology is essentially the study of the origin, characteristics, and development of landforms. Things like mountains, valleys, rivers, coastlines, these kinds of things. And there are essentially, again, two types of forces that produce these that interact and produce landforms. Forces that push, move, and raise the Earth's surface up, and those that scour, wash, and wear down the surface. And so the key point number 1 here is that we have to just understand the general makeup of the Earth. And so when we're talking about things in geomorphology and landforms, we are really concerned only with the very top of the Earth's structure, the crust up here. But, you have to understand, of course, that where a lot of these processes get their energy from is from the energy and the heat that is well inside the Earth because of the fact that we are, the planet has not completely cooled down. There's still some heat in its center from its formation over 4 billion years ago, and that heat radiates and moves and makes the Earth somewhat dynamic, and that heat can make its way up to the surface. And so this is one of the things that kind of shifts the plates of the Earth around. But it's important to note that we're really going to talk about this very top of the whole Earth structure. We're not going to really talk much about the core or the mantle and all this. We're all the way up here. And to give an idea of just how small of a section that is of the whole Earth, this area here of the crust is sort of like the skin on an apple. That's a pretty close analogy. Like if you think of how thick the skin is on an apple, if you peel it off compared to the whole apple, that's like the crust of the Earth to the rest of the Earth. And that's where most of these processes are that we're going to talk about. And so again, this is just kind of a closer up look where it's showing the crust up here, and then you get into some of the mantle areas here. You have an area called the asthenosphere, which is important. This is an area that's very heated, and the rock is very plastic. In other words, it's molten, and it moves, and it's shaped. And then kind of riding on top of that molten area, you have 2 different kinds of crust: oceanic crust and continental crust. And as you'd expect, the continental crust is where the continents are. Oceanic crust is the kind of crust that's underneath most of the oceans. Now, there are islands and things that come out of the middle of oceanic crust, made out of oceanic crust. And so, these are kind of generalizations. But if you look at something like North America or, Africa, these tend to be these large chunks of crust that are a little bit lighter than the underlying oceanic crust. One way to think about it is that these continents, the continental crust is a little bit lighter because of its silica content and other content of other minerals, and they tend to kind of be almost like, maybe this is a bad analogy, but like a raisin stuck on top of peanut butter or something, where what moves around is that, what really is moving around when we talk about plate tectonics is that layer of oceanic crust, but the continents are kind of riding on them sort of like rafts. And again, the reason why the continental crust is on top is because it's a little less dense, and they also the crust on the continents tends to be a little thicker. You'll see why this is important here as we kind of discuss this, talk about plate tectonics and some of the processes that build landscapes. All right, but one of the things we also have to know is the kind of materials that make up the rocks in the Earth's crust. And there are a lot of different ways to classify rocks according to their physical properties, but one of the most common ways is to classify them by how they were formed. And so there are basically three main ways that rock gets formed. And this is referred to as igneous rocks, sedimentary rocks, and metamorphic rocks. And people will talk about the rock cycle, and it's also in the textbook for this chapter, where essentially when you're trying to define what a particular rock is, it's kind of what happened to it most recently. So for instance, you have molten magma or lava that gets erupted from a volcano. That turns into what's called igneous rock when that lava cools. And there are different kinds of rock depending on whether it cooled outside the volcano or inside the earth or those sort of things. But that rock that's all formed from just magma solidifying is called igneous rock. That rock may then get worn down and eroded through processes, broken into pieces. The very fine pieces of sediment go into an ocean and then start piling up on each other layer by layer by layer, and then get buried more and then get compressed through weight and heat. And that will give you what's called sedimentary rock. That sedimentary rock, in turn, as it gets pushed further and further down, and it might have some pressure exerted on it because of the movement of the plates, can melt it a little bit, put it under more pressure, and in those cases you get what's called metamorphic rock. And of course, at any time, this stuff could melt again if it's under enough heat and pressure and turn into magma and then start the whole cycle all over again. And so again, these are the same rocks, but they're going through these different processes, and we define them sort of by what happened to it most recently. So again, these are just some slides kind of talking about those specifics of igneous rock. And one of the main ones being basalt. When we watch that Hawaii video, everything they're talking about there is really igneous rock or basalt, because it's almost all volcanics out there. Sedimentary rocks are pretty identifiable because the way that they tend to arrange themselves in these large flat layers. So if you look at something like the Grand Canyon, this is a great example where each one of those colors is a different layer of sedimentary rock that has kind of different material that was deposited all at one time. And so it kind of over time makes these lines of older, and with the oldest rock on the bottom and the youngest rock kind of up on top. And then you can also get metamorphic rock, where some of the rock was under pressure for a long time, and then these rocks become something else. So like for instance, marble, where there's places that marble is being quarried, that is limestone that has just been under a lot of heat and pressure and metamorphosizes into marble, things like that. Okay, so that's key point number one, just knowing those different kind of rock types. And again, there's more information in the book and the rest of the PowerPoint. Key point number two is about plate tectonics. So the Earth formed about 4.5 billion years ago, and because we still have this heat in the center of the Earth that's kind of driving these movements in the mantle and above, it's making the continents essentially shift and move around. And this theory came about, well, started really in the early 20th century when there was a guy named Alfred Wegener who started noticing that the continents appeared like they might fit together like jigsaw puzzles. Like if you took Africa and South America, it seemed like they once maybe fit together. But there wasn't a lot of other evidence that the continents had been on the move. And the evidence for this didn't really amass until 1960s or so. You started getting more information about when people started mapping the ocean floors and then seeing kind of the ages of different areas, and they could see how these landforms had actually been connected originally and had been moving apart. So at one point in the distant past, all land masses were united in what was called a supercontinent called Pangaea, and over millions of years these continents drifted apart. And so the reason why the continents are moving is because you have this molten layer called the asthenosphere that we just talked about, that the crust sort of rides on top of. And so you get these convective currents, and I'll talk about this here in a second a little more with the diagram. Essentially is what the energy that's where the energy comes from moving these continents around. And so part of plate tectonic theory is that there's different kinds of boundaries between these plates of the Earth. Some are being pushed apart from each other, some are being pushed towards each other, some are rubbing up next to each other, and these cause different kinds of plate boundaries, or what are also called faults, that create earthquakes and also volcanoes. Okay, so some of these things here talked about convergent, divergent. I'm going to show better here with these pictures in just a second. And as mentioned, earthquakes and volcanic activity tend to happen at these plate boundaries. Okay, so again, this is this idea. I'm going to talk about it more with these pictures. So originally there was Pangaea, the continents started splitting apart, and you can see how by present day all the different continents have kind of drifted apart into their present configuration. And of course this is an ongoing process. In the future the Pacific Ocean will get smaller and smaller, the Atlantic will get bigger and bigger, the continents will then collide and and to reshape and all of that as we go forward in time as well as backwards in time. So right now, this is a map that shows the different plates of the Earth. And you kind of look at it here. This is North America, right? There's the Great Lakes. The North American plate is basically moving this way. The Pacific plate is moving more this direction. And you can see the Eurasian plate, which is most of Asia and Europe, is going this other direction. You have some smaller plates like the Philippine Sea plate. You have the Nazca plate off of South America. And you can see that in some places, like... this doesn't show it great, but there are some places where the plates are moving apart from each other. The Mid-Atlantic Ridge is one place where this South American plate's moving this way. The plate here on the African plate is moving the opposite direction, and they're moving apart from each other. But in some places, such as here where the Asian and Pacific plates are coming together, you have a place where the plates are bumping into each other, and I'll talk about kind of what happens there. And then there are other places like the San Andreas Fault in California where the plates are essentially sliding next to each other. And so you've got all these different kinds of movement in the plates. And this kind of shows that a little better, where it shows the arrows and it shows the major boundaries between the plates. And one of the things about these boundaries is this is where you see almost all of the volcanoes and earthquakes. Not all of them, but a lot of them. This is a map where volcanoes that are relatively recent volcanoes are all in black triangles. And then red are where you get major earthquakes. And you can see the vast majority happen to be on these plate boundaries, particularly around what's called the Pacific Ring of Fire here. But other places too. You can see this boundary here, in the Mid-Atlantic, around the Mediterranean, and elsewhere. So the question comes up, okay, what is driving this whole process? And essentially what's going on is you have differential heating of different parts of the Earth's mantle, and it's setting up what are called convection currents. Think about it like when you're boiling a pot of water on a stove, right? A lot of the heat's going right to the middle of the pan, and it's heating that water. That makes the water lighter, and it moves it upward. And then it comes up, bubbles up, and then it comes down, it kind of cools as it comes up to the top, comes down around the sides, and plunges down under, gets reheated again, and comes back up. And so it sets up this kind of a motion, even in like a normal pot of boiling water. The same basic thing is going on a planetary scale, where you have areas where you have the heat moving up, it's spreading the plates apart, and then where the plates come together, usually what happens is they come together, one of them is a little bit heavier or denser than the other, one goes underneath the other one, usually the one that's a oceanic crust kind of goes down, the one with continental crust stays up high, and moves underneath, and you can see here, kind of repeats the cycle. As the plate comes under here, it melts, and new molten material is being brought up here where the mantle plumes are moving upward. And so this is what's driving that whole system. And so in the book, and also in the rest of the PowerPoint, there's some specific diagrams here that show you then what happens with these different types of plate boundaries, of which there are basically three. There's divergent boundaries, and divergent is shown here. This is where the plates are pulling apart from each other, being pushed apart. There are two types of what are called convergent boundaries. Both of them are converging, moving towards each other, but in one, when it's continental crust and continental crust, I think I've got a diagram here, hold on. So sorry, it's kind of skipping ahead. The example would be the Himalayas, where there are two, excuse me while the police go by, there are two plates moving towards each other, they both have continental crust, they hit each other and they just kind of crumple and create giant mountains like the Himalayas. In other cases, like this, what usually happens, like around the Pacific Rim of Fire, is one of the crusts dives underneath the other one when they're converging. And what happens there is you get, first of all, very big earthquakes where this is going on, because sometimes those plates stick for a while and then boom, all of a sudden kind of become unstuck and create large earthquakes that also then create a lot of tsunamis, because if there's water on top of that plate, when it sticks and then goes, it shoves that whole column of water up and creates a giant tsunami in the ocean. The other thing that happens is that you get volcanism here. As the plate dives underneath the other plate, it melts down here where the tips of my fingers are and creates, melts into lava, which moves up through the continental crust, and you get, usually about 100 miles or so from where those plates come together, a line of volcanoes. So let me go ahead and go back to one of the plate things here. This is kind of showing this here, where you get the subducting plate and you have this line of volcanoes. If you look at the map on where that kind of thing happens, The northwestern part of the United States is a great example. You have this converging boundary over here, but you don't get the volcanoes right where the boundary is. You get them inland about 100 miles. Mount Shasta, Mount St. Helens, Mount Rainier, Mount Hood, Crater Lake, all these big volcanoes are a little bit off of that in a line. Same thing happens in Japan, where you have a lot of volcanoes in a line about 100 miles from where the plate boundary dives under there. Same thing on the Aleutian Islands, too. Okay. So, I talked about that. So there's two different kinds of convergent boundaries. Ones that they kind of crumple, one subducts. You have a divergent. The other kind of boundary is called transform, and that's where the plates are just moving past each other. They're not hitting each other, they're not pulling apart, they're just kind of grinding past each other. And that example of that is like the San Andreas Fault in California. And there, where the San Andreas Fault is, you don't get a lot of volcanoes, but you do get earthquakes that happen from just where those plates are sticking. Okay, so I had kind of meshed key point number 2 a little bit with key point number 3, in that I talked a little bit about how those plates then create landforms like volcanoes, how you get crumpling like in the Himalayas. And so I'm going to kind of, again, just briefly show, this is that side view version here showing what happens with the crumpling. This is a convergent zone. The other thing that happens is where you get these spreading areas, right, where the divergent boundaries are happening, you get volcanism there too. So there are some places, a lot of the places that are spreading are under the oceans, like the Mid-Atlantic Ridge, and Iceland, which has a lot of volcanism. But also one of the places you get a spreading boundary is in East Africa, the Great Rift Zone, which is essentially really it's a rift. It's East Africa sort of pulling apart from the rest of Africa, and that's where you get like Mount Kilimanjaro and some other volcanism there. Okay, and as you'll see, in other parts of this PowerPoint and in the chapter, many building process of landforms are the result of these plate movements, like volcanism, like uplift, and the associated hazards like earthquake and tsunami. All right, so last key point. There are forces that erode landscapes. Wind, water, in the form of rain, rivers, or oceans, as well as glaciers, carve and move against these mountains and make them smaller, right, create river valleys. So other kind of landforms are the result of, after these things have all been built up, how do they start getting eroded away? And so usually this happens through 3 major mechanisms: weathering, mass movement, and erosion. And with weathering, there's a couple different types of weathering that's important to kind of note here. And those 2 are mechanical weathering and chemical weathering. So weathering is the breakdown and decomposition of rocks and minerals at or near the Earth's surface. And it usually happens from water, air, or just temperature difference. And so, but also you do get, so let me say, so mechanical weathering is essentially these things physically being kind of broken apart or crushed apart. And so things like if it freezes and then thaws, that can break rocks apart. Salt crystals growing in the cracks of rocks will split them apart. Plant roots moving down into rocks will then kind of pry them and break them into pieces. Those are examples of mechanical weathering, kind of physically changing the structure. Chemical weathering is when you get a change in the chemical makeup of the rocks, usually because of the formation of what's called carbonic acid here, or carbonation, where you get carbon dioxide gas in the atmosphere, dissolves with water, forms a weak acid that starts eating away at the rocks, and then that's a chemical weathering, but it also aids also aids the physical weathering in that it will weaken the rocks and make it more prone to roots being able to go through it, or other kinds of things that might split it apart. So water, also oxidation. In the Hawaii video, you'll see what happens when lava, which is very, very hard initially but has a lot of iron in it, is exposed to oxygen and water, and it starts to rust, and the rock itself gets very, very brittle through time. So that's an example of a chemical weathering. The other thing here is, and the chapter and the rest of the PowerPoint gets into this a little bit more. You also have just erosion, right? Water just running over something over and over again, just kind of carrying away particles is one way that large forms get smaller. And also mass movement, which essentially is just where you have things like landslides or mudslides or avalanches, where a lot of a landform all of a sudden breaks off and just falls due to gravity. So there's different ways in which these things waste away. Okay. So this is the end of the key points. So just be sure to read the whole chapter, check out the rest of the PowerPoint, watch other video links for other important information. I think the Hawaii video really brings together the processes of plate tectonics, landform building, and erosion into one single case study. And there are some optional video links in the rest of the PowerPoint. You don't have to necessarily look at them, but if you have some questions about how some of these processes work, the videos can give you a little bit more background. So that's it for today, and I will see you on the next module.